Now we shall study the about the much more detail about the mezzanine floor structures and how they are usually made in Australia. So we can go to the mezzafloor website .com.au, and in on this website they do have these excellent pictures showing that how they are modeling and how they are designing the mezzanine floors in Australia. So one of the pictures here, this is the first picture, and in this picture you can see clearly that the columns that they have selected are the box columns, and on top of that they have selected a hot rolled UB girder, and on top of that they have selected these C purlins, which they have closely spaced with each other and approximately at a spacing of 500 mm center to center. And there is one more picture here. Here also you can see that how they have selected the box column, and on top of that they have put an eye girder. But the only difference between this picture and this picture here is that if we are seeing the top of the eye girder, in this particular case the top of the eye girder and top of the C purlin, that is same. But in this particular picture, here you can see that how the C purlins are resting on the top of the steel beam. So that is like the two different types further if you want to see. And the connection, obviously, we can extract a plate from this particular I beam. And from that, we can, simply put or fasten our two M16 or M12 bolts as per the design. So here also you can see that the picture. One more thing I'd like to add here is that here you can also you can see that this is a cantilever part. So it is not that the we can say the mezzanine beam is like getting supported from the left and right. Here you can see that there's a little bit cantilever also on the extreme edge. And here also you can see the picture that they have installed a staircase here, and what they have done is that to support the staircase here, they have added these two columns here also. And to support these two columns aesthetically or architecturally, they have added these, we can say, mesh also on the left side and right hand side. After that, here also you can see the important picture here. The important thing here is that here also you can see that the SWLL limit, that is the live load limit, that has been considered as 500 kg per meter square. So it is to ensure that the loading on the top of that is not exceeded above this particular value. So that is a good thing. And here also you can see that they have added this picture on both the side, that is on this side also and on this side also. Similar board also you can see here. So here also they have given a warning that the live load, here also you can see that there's a lot of storage on the top, but at the end you can see that their responsibility is only up to 500 kg per meter square, and it is never recommended to exceed that capacity. So here also you can see a picture. So here also you can see that the maximum live load limit capacity has been shared. So that is one thing. Second thing, here also you can see that how they have installed the railing. Now railing is not like simply anchored or screwed on the C purlins. On the top of the C purlin, what they do is that they do install the wooden laminate, and on top of that they screw their particular handrail system. So I hope the concept is clear to you. And here also you can see that the on the top of the columns you can see these hot rolled eye girder, and on the top of that this UB uniform beam you can see a cleat. This is also known as cleat, and from that particular cleat they have fixed these two bolts here. Now, just to give you a second example of how to design the mezzanine floor structure, we can try to model this particular case. So, the copyright of these pictures is with mezzafloor.com.au only. So, they are the owner of these three pictures, and they have done these projects in the Australia. So after that, if we want to design the mezzanine floor as per this particular case. So as an example, we can select this particular case. So let us assume that the typical framing looks something like this. And let us say we do have these, we can say three frames here. These three frames, basically we do have these Z purlins also getting supported on the top. And let us assume that this particular cantilever that is coming on the outer side, that is approximately, let us say, 1500 mm, and obviously that is being closed by the C purlins. So if we want to design this particular case, let us assume that this spacing is approximately 4.5 meter. This spacing is again 4.5 meter. Or sorry, what we can do is that let us assume that the spacing is 6 meter only. This spacing we can assume it as 4.5 meter. So what we can do is that we can start this modeling in the ETAP software, but before that, we do need to find out the effective size of the purlin for which our system is safe, and we do need to find out this particular spacing also. That is what exactly is this particular spacing, which is optimized also and safe also. So usually, as per the standard practice, we can take this spacing as 0.5 meter. So dead load, let us assume that that is in the range of 100 kg per meter square. Live load, let us assume that it is approximately 500 kg per meter square. Now the spacing that governs our design, let us assume that that is approximately 0.5 meter. So after that, we do need to find out the UDL here. For which our purlins needs to be designed. So let us assume that this particular spacing is 0.5 meter. So UDL for dead load, that comes out to be 0.5 into 1. That is 100 kg is nothing but 1 kN per meter square. And this is approximately 5 kN per meter square. So dead load where UDL comes out to be 0.5 kilonewton per meter, and live load UDL comes out to be 5 into 0.5, that is 2.5 kilonewton per meter. So we know that this we do have one cantilever span of 1500 mm, and these two spans are 4.5 meter. So let us just try to model that in the first of all try to design the purlins here, that is the C purlins. So we can select open the X Factor software, and then here we can select X Factor C purlin. This is our case where we are having a cantilever span on the left. So number of spans we can we know that in our case that is approximately 2. So we know our span as 4500 mm, and we know that number of spans here are 2. So if we are checking that, we do know that we are missing a cantilever part here. Yeah, now it is okay. So here we can select number of spans as 2. So sorry, we do need to select it as 3 here. Yeah, now it is okay. So we do have this span as 4500 mm, this span also as 4500 mm, and this span on the left, that is approximately 1500 mm. So on the left we do have 1500 mm, and on the right we do have this 4500 mm span. Regarding the bridging, I just want to show you this picture here. So here also you can see that this is also of mezzaflow.com.au. Here also you can see that this is a bridging arrangement. So this bridging has been done in the purlin because our loading must be very high here. So that is a typical example of how the bridging is made in the C purlins for mezzanine flooring arrangement. In the remaining picture, there must be bridging, but it is not visible. So this is an example where you can see clearly the bridging. So let us assume that for optimization, we can select one bridging for each particular case. Default bridging, we can select it as yes. So after that, restraint from sheeting attached directly to purlin, we can click it as no. Find purlin size, that is also okay. So here we can add the dead load first of all. So for the dead load, we can select UDL load, and UDL value comes out to be as we have selected. So UDL value for dead load comes out to be 0.5 kN per meter, and for live load it comes out to be 2.5 kN per meter. So we can select here as 0.5 and for all spans. So that is also done, and after that we can select new PLC as primary load case. We can take it as live load, and here also we can select the value as 2.5 kN per meter and value for all spans. So now this is okay, and after that we can go to the combined load case option here. So we can select new CLC. We know that for dead load the value is 1.35 times the dead load. So we can name it as 1.35 times DL. And after that we can again add click on new CLC. For that what we can do is that for 1.2 times the dead load and 1.5 times the live load. So we can name it accordingly. That is 1.2 DL plus 1.5 LL. And after that we can add the serviceability load combination also as 1 times dead plus 1 times live. So this we can name it as 1.0 times dead load plus 1.0 times live load. So after that we can select all of the combined load cases. We can left click on OK, and we can left click on calculate. So we can left click on moment capacity design here. So in here we can see that the Purlin that is safe as per the calculation is approximately, we can left click on one solution here, and so the Purlin that is safe is 150 into 2.4 mm thickness. So let us say that if we want to use the 200 mm size Purlin, so we can left click on return to editing spans. We can left click on check Purlin size, and here we can select the Purlin size also. So we can left click on 200 1.9 mm thickness. So we can left click on calculate here. So for 200 we can left click on moment capacity design. So here we can see that our system is like safe here. So the ratio that is coming is very low. That is only 0.11 is the utilization ratio. So more or less we can say that this is safe, but on a very conservative side. So just as an example to show you, what we can do is that we can select 200 into 1.9 mm thickness also, or we can go here and select 200 into 1.2 also, and then check that what exactly is are the margins while designing. So here you can see that now it is failing in the design. That is the ratio is coming as high as 1.5. So instead of 1.2 we can select 1.5, left click on calculate, and left click on moment capacity design. Still it is failing in under the case of 1.2 times the dead load plus 1.5 times the live load. After that we can select 200 1.9, and here we can see that now the ratio is like 0.73 under the case of 1.2 times the dead load plus 1.5 times the live load. And for serviceability our utilization ratio is approximately 0.5. So this is also okay. So it is not that we can opt for 150 into 2.4 only, we can opt for 200 into 1.9 also. So if we are reviewing the unit weight, so here we can see that for 150 into 2.4 size, our unit weight is approximately 5.67 kg per meter. But under the Purlin that we are selecting, that is approximately 200 into 1.9, that is approximately 5.74. So there is no as such difference here. The difference is only, I think, of 70 grams only. So that is like very less. So what we can do is that we can opt for 200 into 1.9 again. One more thing I'd like to add here, that if we are selecting the Purlin sizes, instead of selecting 150 into 1.9, which is having 4.51 kg per running meter, we can opt for 200 into 1.5, which is having again 4.5 kg per running meter. So by selecting the higher section, we are reducing the weight also, and again you can see there is a substantial difference in the section modulus also, or the strength of the section also. So always proceed review this particular table. So similarly, if we want to select let us say 200 into 2.4. So instead of selecting 200 2.4, which weighs 7.21 kg per running meter, we can opt for 250 into 1.9, which for which unit weight is 6.5 kg per running meter. So this is how you can do the optimization, by selecting the higher sizes and by selecting the lesser thicknesses. Review the design. So one thing is clear here, that we can opt for C purlin here of 200 mm depth and 1.9 mm thickness. So C200 19 is our final purlin size. That is, this should be in the range of 200 mm and the thickness should be in the range of 1.9 mm. And the spacing between the two purlins, that is approximately 500 mm, or we can say 0.5 meter. So that is now concluded as per the design requirements.